So can you, so it's a great pleasure of mine to introduce our today's speaker. We're looking for a talk by a prominent mathematician, Georgy Borisovich Shabat, and he's going to tell us about the beautiful construction due to Alexander Grothendieck, dessins d'enfants. Let's welcome.
Okay, now I'm trying to organize the whiteboard, and please tell me whether you see it.
Not yet.
Not yet. Mhm. So, and now
Yes.
Yes.
now you are, yes. Okay, okay then. So today I'm going to speak about the very foundation of the theorem. As we heard, it is usually mm, uh, pronounced in French, those speaking English. Dessin d'enfant. Some people call it child's drawings, but we are used to Grothendieck's terminology. So, as I have promised, a brief history will be told now. This is a rare example of the theory that has quite a definite author, Alexander Grothendieck. So a couple of words of his activity before 1972. He was one of the most prominent mathematicians of 20th century. He re-founded algebraic geometry. In fact, having tied it with commutative algebra, that just changed the subject completely. Then he introduced the L-adic cohomology. That was his contribution into the dream of André Weil, who formulated, oh yes, is it correct?
Everything is visible.
So I've got a message that,
Everything is visible.
sorry, say it again, please. Do you see my white?
Yes, we do.
Oh, okay. Okay. So the most important part are dots, because I quote just two of his main contributions. Just a couple of words about this Eleatic cohomology. In the middle of 20th century, André Weil suggested a theorem of quite a unique form. It was about Diophantine geometry, number theory, that he would like to relate to algebraic topology, um, just activating the intuition that had seemed nothing to have in common with number theory. And for that, he listed the axioms of the non-existent theory, of the cohomology theory of arithmetic varieties. And Grothendieck created such a theory and did lots of other things. But in 1972, Grothendieck left the mathematical community by some reasons that had nothing to do with mathematics, and perhaps we're not going to discuss it now. There are lots of sources considering from a different point of view. So he left Institut des Hautes Scientifiques, where he worked, and returned to his the university of his youth in Montpellier, where he had to work with students with almost no background. So he had to choose the topics not demanding any background, in sharp contrast with what he was used to working in Paris. And what he could suggest is the topic of, maybe I use other color to mark it somehow. It doesn't work. My color doesn't seem to work well. Background, so, oh no, it does, but not in the way I'd like to. So this topic was studying the embedding of graphs into surfaces. And he became interested in the topic himself, developed it somehow, so it was about a half of this period until 1978, and I'll start today's lecture reproducing it. So it were quite elementary considerations, and really to participate in it, the students had just well, to have some artistic qualities, just mostly drawing and fixing the result. Elementary. So in terms of today's lecture, they were So they will be called, as Grothendieck suggested, dessins, and these activities related dessins and group theory. It turned out afterwards that the contribution was not original at all, and the experts in combinatorics and in topology knew this technique, but Grothendieck has suggested new and nice terminology, and since then it was widely accepted. And then in the middle of this period, 1978, um, an important event happened. So Grothendieck was informed. Well, he did not completely stopped all the relations with community. And for instance, as far as I know, this was the information I'm going to tell you about was delivered by Pierre Deligne. Something happened now about Gennady Belый. Gennady Belıy's.
And what was Gennady Bely's destiny? Was he popular in the Soviet Union? Did he immigrate? What happened to
No,
him?
he did not. He was a very shy person. I knew him well. He was of the same background as myself um, in Shafarevich's Moscow School of Algebraic Geometry. And no, he died untimely at the age of 50 and a bit. And well, what else did you ask about? So he did not emigrate. What was the question? Ask it again.
Yes, he was a Shafarevich school. Yes.
Oh,
Okay.
yes.
Yeah. Okay.
So I think I will formulate his result in the second lecture, maybe not today. But what was important for Grothendieck is that it demonstrated the relation of this elementary theory of dessins with arithmetic geometry. Arithmetic geometry, the domain of mathematics that Grothendieck was trying to abandon. And therefore, it became clear to Grothendieck that his fate told him about the inavailability to work in his mother part of geometry. So he he developed this theory as we know it now, and this was the year 1984 was the year when he tried to return to the official mathematics, and he presented a unique text as case down program, which is not a mathematical text. It has almost no precise definitions or theorems or proofs, but it contained lots of ideas. Unfortunately, and well, he used it as well as an tried to use it as an official document to return to the structures, and unfortunately it was rejected. And after that, for a long time, Grothendieck continued his work in almost complete solitude.
So,
And
was it possible
produced several other very
was it possible in France to reject Fields medalists?
yes, it was just because, well, I've heard certain details about that, but they contradict each other. Um, well, just now there is a so-called Grothendieck circle working in France with lots of details. So I'm not sure I can give any informations by information. But by the way, for several years, I met the reaction of prominent mathematicians who just asked me, was it a true, a true mathematical paper or just a text by a crazy person? Because it did not at all look like the usual document. So, anyhow, Grothendieck was out of this theory. The theory he suggested and thought about other things, and then the first document, the first usual mathematical paper that was devoted to it was the paper by myself and Voevodsky, drawing curves, devoted to Grothendieck's 60th anniversary and published in the corresponding volume. And by the way, we have sent the draft to Grothendieck in some complicated way because Grothendieck stopped the relations, as I said. But some French mathematician who used some ways to send it to Grothendieck, told us that Grothendieck will speak with Soviet mathematicians. So he was mostly against the bourgeois society. And really he answered us in a very polite short note in which he wished us all the success and then wrote that unfortunately he would not give any comments of mathematical character, as he wrote it, because of more urgent matters in this short life. Well, the life for him turned out not to be really short, and he lived until almost 90 since then. But the developed. Theory developed, and now there are hundreds of publications, and there are lots of things to do. Perhaps the main goal of my lectures will be just demonstrating that anybody who is looking for the domain where some creative approach can be realized in mathematical result can try to work in this domain. So
Excuse me,
maybe
did he know, was
maybe
he was he aware of the work by Bailey?
yes, it just happened. It happened. It was just the turning point that I was trying to mention. And I'll describe the mathematical part of it soon. But it is not so elementary as what I'm going to speak about today. I don't know whether we'll come to it today, but in the next lecture that is planned in a week, I think I will speak about it. So this is the end of the general part. Perhaps it's time now to ask you whether there are any questions. Okay, then I turn to the elementary part of the theorem. And I'll use a non-standard term pre-descent. And it is a triple x0 in x1 in x2, where x2 a compact surface. I mean a topological manifold, so without border. And x1 a graph that I'll
Excuse me, I don't see what you're writing.
I should you don't see the next page, or should I
I
write?
don't see the next page. Yes, I see only one page.
So what should I do? I've pressed my button add the page and nothing happened. Now
Mm.
I'm on the third.
Well, we see the first page only.
So how do we solve this problem? Well, one of the approaches is that I write only on this page, and maybe I can erase everything, but no. Any technical ideas? So what can I do really? I don't know. What I can try is erase what I've written and well use it just as one. Uh, well, I'm suggested to leave the whiteboard. Has it been copied? Well, let me try. So I press it and try the next attempt. Now, as for do we have mhm. Well, sorry, I see only the previous whiteboards. So let me try again. I'm sharing it. It does not work. Just again. Here I'm trying the new one, sharing it. I'm suggested to continue. Now I'm sharing it again. A new one. Do you see a new?
Yes, we can see your whiteboard.
Okay, so then I'm not trying to keep it, and perhaps I don't press the new whiteboard and just use what I have and erase it as if I was in the usual room. So again, now I repeat what was written there and use predecessor, but now I'm asking you, do you see it? Predecessor. Do you see these words?
Sorry.
Predecessor. I'm right, and I see your. I'm writing the triple now. So I need to know, do you see it? My x0 in x1 in x2. Please, somebody.
Yes, yes, I
Yes, you
see.
do. Okay. Okay. So x sub 2 is a compact surface. And then x naught is a finite set, non-empty, finite, sorry, finite set, and it is supposed to be non-empty. And then I give a definition of a graph in a bit non-standard form, that the complex x sub 1 is a graph, but I give it in a bit not non-standard form. So x sub 1 is such a subset of a compact surface that the complement is homeomorphic to disjoint union of interval, and the main demand to the whole triple is that in the same way x2 minus x1 is, homeomorphic, and here it is homeomorphic to the disjoint union of open disks. It is called the pre-descent just because in the main part of the lecture we'll assume that the surface is oriented, but for some part we do not assume it. And part of the group theoretical description still works. So maybe some non-example is in order. Non-example would be if x sub 2 is a torus. And we'll try to err the rule to use green color for the graphs and red for the vertices. So it is not a descent by the obvious reason that the complement is homeomorphic to the cylinder, not to the union of disks. And well, in order to have it as the sun, we draw the larger one.
Excuse me, it is not a descent, but is it a predescent or what?
And not a predescent, because the second condition is violated. The complement is homeomorphic to its cylinder.
Okay, but am I right that the only difference between descent and a predescent is the orientability?
Yes, that's correct.
Okay.
So, but what I'm trying to draw now, maybe the better position would for the vertex will be here. So we need at least two arcs to turn it into the song. Like this, I hope it is clear, and it is just a standard realization of a torus. So I erase the words non-example because it is crossed out, and this is a descent. Well, and it is the standard realization of a torus as a square. Maybe I draw it near this. It is the most standard realization of the square. Oh, the colors are wrong, sorry. The square with the unique vertex and with the identified opposite signs. And now to give an example of a predescent that is not a descent. suggest what I'm not going to draw completely. That is the icosahedron. Icosahedron. I am just trying to draw the top. And so on, factored by the antipodal identification. Podal. So podal. So we'll find some graph on the projective. Oh, something has happened. My whiteboard has disappeared. Am I still in contact?
Yes, you are.
Now I'm promised the new whiteboard, but it is empty for me.
For us too.
So here is what I see is the new one. That's what I'm writing. Yes, and here somebody is leaving the traces. Well, unfortunately, the technique today seems not to be perfect. But I'll try to continue. So the last predecessor that I was going to present can be described in words. So imagine an icosahedron that we think about as projected to the sphere in which it is inscribed, and let us identify the antipodal points of that square and get into the non-orientable surface, the projective plane over reals. And then icosahedron will be a graph on it. And the complement to this graph will be the disjoint union of triangles. Is it correct? So I try to start something new here with the hope that it does not disappear in a while. So we turn to the group theoretical description of dessins. We introduce the set of flags, or in other notations of F0, 1, 2 flags, since we are going to consider the other ones as well. So this I'll just draw what it is. Now from now on I'll use no color. So the set of flags is the set of mutually incident triples. The vertex, the edge incident to it, and the face incident to the vertex. And let's consider the whole diagram, and let's consider the other type of flags as well, F01. So we are considering, we mean that some predecessor is given, and obviously the 0, 1 set of 0, 1 flags is like this, and 0, 2 flags are like this. A vertex incident to a face, and 1, 2 flag is the set like this, and F0 in the same style is just the same as was X naught, the set of vertices, and F1 is the set of edges, and F2 the set of faces. And we have the whole diagram of projections. Sorry, what I'm speaking about now is the intermediate step to the group theoretical description of it. So we have the projections here and here and here, the tautological one, just forgetting one element of the triple. And then we have the next, the lower stage of it, again with the forgetting edges like this, and like this, and like this. And I hope you see the piece of a cube, and I complete it with something trivial, with the projections like this, and perhaps call it the cubical diagram of a descent. Now, sorry, one projection is lacking. So there is kind of a theorem. I can not choose theorem that adds any descent can be restored by its cubical diagram. I'm not going to give lots of proofs in my talks, but just the hint is like that. Hint is just associate the triangulation, how do we call it? Simplicial, abstract simplicial shell complex with vertices being the disjoint union of everything f sub 0 and f sub 1 and f sub 2. And then we connect two elements of this set by an edge if they come from the next floor, and connect and define the triangles or the triple of them if they came from the same flag on the surface. And it's an exercise to draw a descent and insert the simplicial complex there. So what is really important here is that we suggest a machinery that fixes a descent in a finite amount of information. So we have a diagram of finite sets. So, for example, starting from here, we can store our descents in the computer, or think about computer programs that will produce all the descents of bounded complexity. So perhaps we don't go there anymore. Well, and now I have a technical question to the organizers, so I can once again try the new whiteboard or erase something here and continue. What would be the solution?
Maybe you can move your whiteboard. No?
Can you please say it louder?
Maybe you can move your whiteboard somehow.
Oh, it's possible.
Yes, I
Yes.
think it's possible. Yeah, I can move your whiteboard, by the way.
So
Excuse me.
how do I?
There is a button with a hand. So this is the way I press this button.
Yes, now I'm looking for the button with a hand, and
Down.
unfortunately don't see it. I see some. Oh, yes, very good. So I can even do it reasonably. So now at my disposal, I have just one whiteboard, but infinite, but an infinite one in the horizontal direction, yes? So starting from now, I can, I hope, start the group description of it. And we introduce the cartographic group. It is perhaps the Grothendieck's invention, graphic group, just by its finite presentation, C sub 2. By definition, generated by 3 involutions with the relations, so all of them are of order 2, and the
By
ones...
by the way, I think we haven't yet scheduled your second talk. Maybe you can we can fix it now.
I thought it was planned for March 11th, wasn't it?
Let me see. I think I'm afraid no. I'm afraid that for March 11th we have another speaker.
Okay,
And
then it's going well. Then I have 40 minutes more today, so I'll tell you what I'll have what I'll be able to, and then continue in some other day we suggested. Is it okay? Is it okay?
yes, okay.
Mm-hmm. Okay. So what will definitely be possible that the definition of dessins in group theoretical terms. So we make this is a universal and of course infinite group, and we are going to define its action. Sorry, I'm using my personal notation, acting for a group acting on a flag. So, given a flag that I draw like this as a triple, we define these involutions as changing the elements of the flag over the dimension corresponding to the index. So sigma sub 0 keeps the edge and keeps the face, but changes the vertex. Sigma sub 1 keeps the vertex, keeps the face incident to it, but here is I have some problem. No, sorry, it is just the reflection, of course. Mm-hmm.
Am I right that these are just generators sommet, arrête, and face, sigma, alpha, and phi?
Say it again, please.
So am I right that these are sigma, alpha, and phi, sommet, arrête, and face? As it
No, no. These other notations with French indices are related to the oriented surfaces that will be discussed later. As far as I heard your question, but sorry. Oh, yes, I don't know why I was afraid of what I have written. So what we have, maybe I change it a bit. So this is the fixed edge, but there is another edge, another one. Well, let it be orthogonal. So sigma 1 will turn it into this one. And sigma 2 will be the reflection. Our descent has no border, so it will move it here. And it is a nice exercise to, that all of them are involutions is obvious. A nice exercise is to draw the commutativity relation. And well, here I maybe just write something provocative. You can automatically think about multidimensional not generalizations, but analogs. Something like that has been done by Grothendieck's students after he had left them, but I don't think that the theory in higher dimensions is really completed. And now I want to, so here is my hand, and I try to move it, but it does not. Oh yes, it does. So I just show how we restore the cubical diagram by this group constructions. So perhaps we better do it element wise. So what are our vertices? Nothing but the set of, oh no, first we use double flags. So what is a double flag? Let me draw it maybe here. And it is what is fixed by the reflection against it. So it is whole, the vector of the whole F by the two-element group. Oh, whatever. Some curve appeared on the screen. Can you please delete it? Or maybe I can erase it. So, we have to factorize it with respect to sigma 2. Yes, this is what is the common part of it. And so on. F0, 2 is the factor of F by a two-element subgroup generated by sigma 1. Now I'll draw it here. And F1, 2 is F factored by the remaining one. Well, I'm writing it automatically, and then let's think. Yes, this is the part of it stable with respect to this involution. And then we have the elements like this. What is F sub 0? It is the F, the set of flags fixed by the subgroups generated by so sigma 1, sigma sub 2, and in the same way f sub 1 is, well, not is, but is, say, canonically isomorphic to f over sigma 0, sigma 2, and f sub 2 sigma 1. And there, at the bottom of the cubical diagram, we have the trivial element f factored by the whole group generated by all the three elements. Well, again, it deserves some thinking and drawing that I leave to the participants. And perhaps I'd like to give some application of this technique. Application. Before that, maybe let us discuss the most ancient predecessors or dessins that are platonical, platonic solids.
Excuse me, I have a hard time understanding these maps, sigma 0, sigma 1, sigma 2, and what they do. Do they basically change at least sigma 1, change the orientation on an edge?
Oh, no, there is no,
edge.
for the time being, there is no orientation. Now, look, discuss sigma 1. Thank you for your question. I really am not sure what is clear here and what is not. So discuss sigma sub 1. Yes. So we have a flag here. And it is tempting to think about the other edge here as a result of a contrary clockwise rotation. But we don't use the global geometric concept in defining it. We just have this piece of a surface. Here we have the piece of a surface. It's a polygon, just bounded by a set of edges. And this is another one that that is incident to the fixed vertex. Did I clarify anything?
I understand the picture above. So then sigma 1 maps.
Maybe I add, let me add something new.
Okay.
That will hopefully clarify the situation. But I cannot do, I'll try to do it here. So our x2 minus x1 is the disjoint union not just of disks, but of the polygons. Yes, that's it. The element, in fact, the loops are allowed, but not for this explanation. So when we delete the graph, we get the disjoint union of polygons. And it is not a matter of orientation of it, but just applying sigma 1, we are using the other edge incident to the same vertex. Did I clarify the matter now?
So it's actually changing the flag
Yes.
itself. Okay. Yes. Yes. Thank you.
Welcome. So what I was going to say about, maybe I change it a bit. No. So let's call it generalizing Platonian solids. So our set of flags are homogeneous. So
Am I right that so far
I'm
we're
afraid
not
that I
talking
have.
about any complex structure so far, right?
Oh, no, we are very far from complex structures. But sorry, I have forgotten to assume that, let me edit now, that X sub 2 is connected. Therefore, the set of flags is homogeneous with respect the homogeneous set of the cartographic group. That means that it is the factor of the cartographic group by the stationary element of any chosen, any arbitrary flag. Just the general construction of them that is correct, true about any action, any transitive action of a group on a set. So Platonian is something close to the fact that this arbitrary set, this stationary group, is normal in C2. Well, and now for a beginner, it is maybe not so obvious that in higher genera and on the surfaces of higher genera and their non-orientable surfaces, there are lots of Platonian dessins.
Excuse me, and can you give examples where the group is not normal?
I would say any, thank you for this question. The metaphoric explanation of the term Descendamfang is something like descent drawing, like a child really drawing something random. So if you take a random descent, it will not be Platonian, but you asked for an example, so let me give it the same, just the same picture. Sorry for the titles, and just add one edge. Then it is not going to be Platonian. The characteristic property of Platonian The sense is that, all the elements look the same. In particular, every vertex is incident to the same number of edges, but here this one is incident to one edge, and the other one, it is the same to the five of them. So this is the answer. I was trying to say that it is not immediately clear that there are lots of them, but even the stronger statement holds that I'm going to explain. I have some problem changing colors. It works not like, yes. So the stronger statement is that any descent is covered. I have not defined the morphisms of descents. Of course, descents form a category, and it is a rather boring matter to define the morphisms in topological terms. There are some homotopic classes that preserve that and that things. But as soon as we have defined the category of descents as equivalent to the sets with the action of cartographic group, then we have just the usual structure of category of the sets with the action of a fixed group. So covered means the surjective morphism is surjective morphism in the resulting category. So covered by a generalized Platonian. And the trick is very simple.
And what is a generalized Platonian?
Let's give it the definition here, that the automorphism in this category is the group of automorphisms is transitive.
And what about generalized Platonian, which are not Platonian?
The group of automorphisms of F is transitive on F. For an arbitrary descent, the group of automorphism is trivial, and there is the equivalent.
And what's the difference between generalized Platonian and just usual Platonian?
The usual Platonians, there are just 5 of them, and in genus 0. And they are the result of classification, known for thousands of years. But let me give an equivalent definition. It is just that it is here. The equivalent definition is here. We mark it with a star, that the stationary group is normal. So this is the equivalent definition. And the proof is just So maybe we change the concepts a bit.
When you
So
say
change.
stationary group, sorry, when you say stationary group, you mean the subgroup of C2 that fixes F0, right?
Sure,
The
sure.
stabilizer. Okay.
Stabilizer, yes. It is a better expression. So maybe we change the notation a bit corresponding to our notations with Voevodsky. In some sense, the theory is about fixing the subgroups of cartographic groups of finite index. In fact, Voevodsky and me used this letter B and call these groups the Borelian ones. Just with in the analogy of the linear case. So in the matrix group, the Borelian groups are the groups that fix a flag in terms of linear algebra. But Serre disliked this explanation very much, and I stopped using it for some times. So it is a small exercise to formulate the conditions of on the subgroup of finite index that defines a descent, but it can be done. So the category of descents becomes equivalent to a small subcategory of all the subgroups of finite index in the cartographic group. And then I return to the explanation of it, just the initial Borelian group should be replaced by its intersection with all its conjugates where C runs through the whole cartographic groups. So this is a way to have lots of Platonian-like descents in a purely algebraic way. Perhaps before I ask you about any questions concerning this construction, I suggest an example. Well, sometimes my hand. Oh, yes, it works. It works. So as for the simplest example, for the simplest examples. Mhm. Together with some terms. Well, since I'm not used to non-oriented surfaces, I give the examples on the oriented ones. So the genus is 0 or x2 is a sphere, and we draw we think about it as about a plane together with the infinite point, and we draw examples just on the finite part of the sphere. Suppose we have a North Pole deleted. So together with the names, there are chains like this, simplest examples, and stars. So both are not Platonian-like, because here we see the ends. The ends are special, and here the center is special. So a nice exercise, I think, is the C2 description. And what should be called the Platonization. Informally, we see, well, let me give the answers, and perhaps we are close to the end. Answers. The first one is, I think, intuitively clear. The corresponding Platonian thing will be, I reproduce it in the original colors. So is what we see with the dihedral group. I'm not sure that I'm able to draw the vertices on the unseen side of the sphere. So it will be like this. Think about it geographically as about the equator. So for this, and the second one is by no means trivial. The star is covered by something. The platonization of the star is something. And just to sound enigmatic, I relate it to our future stories about arithmetic geometry, and it is related to Fermat curves. I use the plural because I don't fix the number of edges. So just without knowing anything about the relations with arithmetic geometry, you can have an idea of a combinatorial object that is canonically related to the Fermat curve. So I think I more or less stop here. We have 5 minutes more, or maybe some background and questions and remarks.
Okay. Are there any questions or comments?
Is there a particular reading to go along with the material you presented?
Sorry, I'm not sure that I heard you. Do you want me to share some plans?
Recommend things to read along with the lecture to understand it better, maybe.
Sorry, I haven't heard the beginning of your sentence.
Let me. Is it clear now, the voice?
A bit better, but not so clear.
Okay.
Maybe you just speak slower.
Oh, okay. Maybe I can type in the chat.
Oh, yes, I'm looking for it. Not yet. Recommend some reading. Yes. Well, the obvious recommendation is just reading the article by myself and Voevodsky that is available. And I have reproduced the very beginning of it. And the one that assumes only some knowledge of topology. And it is not an easy reading. Oh, yes, I know, there is a good recommendation. There is a paper by...
Is it equilateral triangulations of Riemann surfaces?
No, it is what I've drawn. Drawing curves over number fields.
Okay.
In the Grothendieck Festschrift. And there is a very elementary introduction by myself and Zvonkin. Zvonkin is a great pedagogue, plain trees. So the whole text is about the twice particular case of what we were discussing. Twice because the genus is zero and the complement of the graph consists of the only disks. That means that the graph is a plane tree and algebraic numbers. This paper is really written for the beginner, for beginners. Sorry for suggesting only my own texts, but there are lots of texts. You can just Google the descent d'enfant and find what seems appropriate to you. And there are lots of kind of informal introductions. The choice really depends on the background. So what I was speaking about today needs basically no background, just just knowing some concepts in elementary topology and group theory, but the whole theory demands more. Okay, then my time is over. So, thank you, welcome, thank you for your attention, and
Okay.
this lecture is not planned as the end of the story about the Sandapang. So we'll.
Okay, thank you very much for a nice talk. I already sent you an email, so I think we have the first open day will be the 25th in 3 weeks.
Yes,
Yeah,
I think it agrees with my plans. So,
it will be great. Yes.
mhm.
Okay. Any further questions? Okay, so let's thank the speaker again for a wonderful talk.
Mhm.